All right, so this section is called the eigenvalue problem for a 2 by 2 matrix. Eventually we'll go with 3 by 3 and then general matrix. But this is a very interesting chapter overall, and it's actually very interesting because we're going back to solving for a system in a weird, interesting way. This is also called Euler's problem because he was actually invented this. But you'll see the eigenvalue, eigenvectors in a little bit. But first off, what in the heck is an eigenvalue problem? So for an n by n matrix A, there are all scalars lambda such that this equation is actually true. Okay? So usually we've done this, where B is some vector. But now, again, specifically just for a square matrix, we can find a lambda that this actually is true, which is very interesting because if lambda is just a scalar, meaning like 5, for instance, what this is saying is the matrix A is literally just a scalar, which is ironically enough, right? So, which I guess kind of makes sense if you just, let's say, for example, this, right? And again, this vector changes however I choose, right? I guess this can be considered a scalar because it's kind of fixed itself. Okay? But again, that's pretty cool because this entire matrix collapses literally just to one single number, which is, interesting enough itself, right? So that's what this eigenvalue problem represents is, can I find a scalar such that this entire A collapses down to one single number? Okay? Which is, again, pretty nice. But the geometric part of what's going on, if you guys are wondering, if they're, if because they're scalars of each other, meaning they're basically the same thing, that means these are parallel to each other, which is kind of awesome. Okay? Now, again, getting a little bit ahead of myself, though. So first, let's go back to definition. So if I could find a scalar lambda that makes this work, that is called the eigenvalue of A. So the eigenvalue is the lambda that works. Okay? And then therefore the vector x associated with that eigenvalue that makes this whole thing work is called the eigenvector of lambda. Okay? So the value itself is the lambda, so that's the eigenvalue, and the eigenvector is what represents this right here that makes it work. So this x here and there. Okay, so they go hand in hand when it comes to this definition. Okay, so going back, what we talked about here is, so because vector is just, x is just a simple vector going across, and since now we show that actually A is really just a scalar, again, that means they're just parallel to each other, right? Just scaling up or scaling down, okay? Which is pretty interesting, right? So all of these lambdas are literally just the matrix A scaling up or scaling down a simple vector. Okay? Now, the whole problem is, well, why is it a problem? Well, that's where it gets a little funky, right? This is far more computational than you probably think when it comes to it, because we got to figure out a couple things now. So based off the equation, there's two things we know. So we know that this is true if I just subtract it over, right? Literally just subtract this over, okay? Now, best thing is, right, I can technically factor out the vector x using this way because it's on the left. Okay. Now, we have a bit of a problem. So since lambda is a scalar, I can't really actually subtract a matrix minus a scalar, right? So it's like saying, again, this matrix minus 2. It really doesn't make sense, right? When we subtract matrices, it has to be the same n by n matrix, right? So we have a bit of a problem. So to do so, we're going to tweak our matrix B, or tweak our lambda here. So what we're going to do instead is we're going to be doing A minus lambda I. Okay? So therefore, we actually have an n by n matrix. So remember, this I is just the identity matrix. So now when I multiply this, now I have an n by n by n by n, so I can subtract accordingly there. Okay? All right, so that is what we care about. So this is the big head honcho. Okay, now this is what we're actually going to be solving for. Okay? So there's a two-step process when it comes to it. First, we got to do is find, well, one, again, the scalars that apply, and next step is find the eigenvectors associated with that scalar. Okay? And that's exactly what we're doing here. So there's two things we have to do. So first we got to find all scalar lambdas such that a minus lambda I equals 0. Okay. Or the proper term is such that a minus lambda I is singular. So we have another property based off that. Okay. So again, what does that mean? That it means the determinant equals 0. Okay. All right, and then next, after that is given a lambda, so given a eigenvector itself, where a minus lambda I is singular. Right, so given the situation we find it, then we got to find all vectors x bar such that this is true. Okay. All right. So now we have a tall order to do, because we have to do two things for each individual question. Find lambda in such a way that this is true, and then find the vector that's associated with that. Okay. Now, the nice thing is, because we start with 2 by 2, finding the determinant is actually pretty nice, because we have an equation for it, right? So just remembering, just means by what singular means. Singular is if and only if the product of the diagonals actually equal to 0, or just multiple, or equal to each other. So in other words, I'll just do it here, right? So 5 times negative 2 minus this times this, right, are the same, or just give you 0, right? That's pretty much the process here, right? That represents if it's singular or not. So we're going to force it to be singular in this situation. Okay? Now, how do we do that? Is first of all, we got to find all lambda that makes this true. And that's exactly what we do. So we just do the A matrix minus lambda I. So it's going to be lambda times 1, 0, 0, lambda. Right? If I distribute the lambda into the identity matrix and literally just subtract straight across, or entry to entry, and hopefully this looks very familiar. Okay. Now again, this means, right, the determinant is 0, or the process is 0. So if I do this times this minus that times that, that forces it to be 0, or it's equal to each other. So we have that times that. Minus 12 equals 0. Okay. So now I got to FOIL all this out and resolve for lambda. Okay. So if I just refoil it quickly, reorganize it, I get that. Okay, and then just straight out factor it again. So -2, -1. So therefore lambda equals +1 and 1. And there we go. So that's how we find the lambdas associated to that. So it's a little harder to do the other stuff, meaning Now find the actual vector, okay? Because now we have to do it twice, once for each individual lambda. Okay. Okay. So now we got to find the vector. So in other words, we first got to do is, so we'll do case 1. So case 1 is when lambda equals 2. So if lambda equals 2, I first got to do this operation. Okay. So this is just going to be that. So again, just subtracting entry to entry. This is going to be 3, negative 2, 6, and looks like negative 4. Okay. And now I just solve for the equation. So in other words, equals 0. Okay. Well, what does that mean? Just straight out do row or echelon form, right? Because we know I equals 0. So let's see what we could do. We can divide by 2 here. And notice you get the same thing. So we get 3, negative 2, 0, 0. So rewriting this, we know 3x1 equals 2x2. So x1 is equal to 2/3 x2. So our vector here, because remember we're going with the actual vector, is equal to x2 2/3 1. Yep, 2/3 1. That's a 2 by 2. Yeah, it's 2 vectors. Okay. Now, usually this is okay, but one process is because we're talking about eigenvectors and eigenvalues. We kind of don't like this. Not really sure why, but I guess it's just notation purposes. We just change it to any arbitrary letter. So I'll just use A for practice sake. So just like that. Or A is some arbitrary number itself. So this is the vector associated with that. So this is eigenvector associated with this eigenvalue. Okay. Now we're just going to do it one more time for case 2. So case 2 is when lambda equals 1. And now we just rinse and repeat the exact same process, but with this situation. So rewriting this is just going to be 1s and 1s here. So 5 minus 1 is 4. Negative 2, 6. Negative 2 minus 1 is negative 3. So this one's not going to fully cancel away. Oh no, maybe we do. Divide by 2, yeah. Okay, so let's do this. I guess I'll just do the long way. So I'll multiply this by negative 3 plus, and then multiply this by 2, 2. So negative 12, positive 6, multiply by 2. So I'll keep the top the same. Yeah, actually cancels as well. Okay. So then for our x1 is equal to positive 2x2. So x1 is equal to 1/2 x2. Right, so the vector itself will equal a times 1/2 1. So again, this is the eigenvector. I'll put just capital EV for short. Eigenvector for lambda equaling to 1, right? The eigenvalue of 1. So let's try a couple more to finish this process off. 2 by 2s are nice because we have an equation. Once it goes a little harder, once it goes a higher order. But let's try another practice problem like this. So again, find all lambda such that this is singular. So again, all you're really doing is this. Okay, so singular, multiplying this out. So 48, I believe. Yeah, it's negative. Okay, and then just rewriting this, so I'll FOIL it and subtract it, and I get something like this. Adding everything together, I get a nice polynomial. The good thing is usually these are going to be easy to factor. I say usually with a hard maybe. Okay, so then straight factoring. So lambda equals, again, 3, 1. Okay. And then part B, same thing we just did for part B up here. We're going to have, again, 2 cases for each individual lambda. So I'll just do 1. So this is 1 lambda, let's say equals 3. So that means it's going to be, I'll just start here, right? Just plug in 3. It's the same thing. So 9 minus 3 is 6, 8, negative 6, and plug in 3 gives you negative 8. And look at that. Hence the reason why 2 by 2s are so nice. You know, they're usually done in 1 or 2 steps. So it's just straight adding pretty much guarantees us our vector right there. So essentially, we get that. So therefore, our eigenvector is of this form. And now we do the same thing for the other one. So plug in 1. 9 minus 1 is 8. This is 8. This is negative 6. Plug in 1, you get negative 6. And again, this may not look overly simple, but it actually is. Divide everything by 8. Divide everything by 6. And notice they actually cancel away once you add them. So this time x1 is equal to negative x2. So therefore our eigenvector is of this form. There you go. There we go. So very short section. That's pretty much it. It's just a brief introduction to the actual eigenvector problem. Obviously, you would probably think it's going to be more complicated as we go on because, you know, this is only 2 by 2s. 3 by 3s get a little bit tricky. You know, we forgot to find, you know, how do we solve for stuff like that for a 3 by 3. But, you know, it's good thing is we've seen this before because this is pretty much, right, how to find the inverse of a 2 by 2 matrix, right? That's basically the bottom of the denominator, what we're doing here, which is kind of nice. Okay. The question is, well, what happens when it's a 3 by 3 or higher? And this can't do anymore, right? So we got to do something different besides of that.